Concepts and Introduction to RBI. In this model, we shall learn about basic risk assessment concepts, introduction to risk-based inspection. What is risk? We should appreciate the fact that literally any activity has some degree of risk. For example, when you take a flight, there is a risk of plane crash, but people take the risk because the probability is so low that makes it acceptable for most people. In fact, the probability of death due to plane crash is statistically far below than the car accident fatality. So it is fair to say that it's safer to fly than drive. Risk is defined as the probability of some harmful event happening and the gravity or consequence of such events. Risk is the product of probability and consequence. Risk assessment is all about determining the probability and consequence of a harmful activity, in our case, metal degradation, damage, and corrosion, and whether it is an acceptable risk or need to be mitigated enough so that the residual risk remaining is below the acceptable level. This acceptance criteria is either set by the owner or determined as per inspection code. Risk management and risk reduction. Obviously, you may wish to reduce the amount of risk as much as possible. Risk reduction is about reducing the risk to an acceptable level. Risk reduction is an activity, is part of a risk management, while risk management is a program. Remember, risk reduction is activity, while risk mitigation is a process of mitigating. It's about identifying the risk management, is about identifying and assessing the risk and then determining whether the risk is within acceptable level, and if not, then have a plan to reduce it to an acceptable level. So that's risk management plan. Evolution of inspection intervals due days. Initially, the inspection and maintenance were merely corrective, that is, inspect the equipment to find the cause and then repair it after the breakdown. Later on, the inspection was based on routine and fixed the time interval regardless of the age and condition of equipment, called calendar-based inspection. Like you take your car for a full service or an oil change every 6 months or 1 year. Later on, it was recognized that condition-based inspection and monitoring is more cost-effective because we would have fewer surprises and unplanned shutdowns. Currently, inspection codes such as API 510, 570, and 653 adopt half-life philosophy for determining the next inspection interval. That is, the next inspection is scheduled when half of the corrosion allowance is expected to remain by that time. There are also other innovation in inspection and innovation techniques developed over the time. For example, on-stream inspection could substitute internal inspection to reduce the shutdown period, but not when there is process-related damage mechanism or when the corrosion is mostly internal. RBI uses a completely different philosophy. RBI is based on the fact that the main object of inspection is to verify the safety and integrity of vessel and report any anomalies. With this in mind, inspection efforts are diverted towards those areas where the highest risk of failure exists, thereby creating a link between damage mechanism and the inspection pattern with the ultimate aim of reducing the overall risk of failure. Please note that according to API 580, failure means loss of containment. RBI may identify equipment and items that do not require inspection or recommend some other forms of mitigation. Through RBI, inspection and maintenance activities can be focused and be more cost-effective. RBI results in a significant reduction in the amount of inspection data that is collected by concentrating on those data that relates to high-risk components and equipment. RBI inspection plans normally result in cost reductions but the prime purpose of RBI is safety and integrity of equipment. So the prime product of RBI is the inspection plan. An overview of risk analysis. A systematic risk analysis includes collect and validate data. Low confidence on non-validated data increase the risk due to uncertainties. Determine damage mechanism, for example, pitting, general corrosion as a result of, say, corrosion. Determine corrosion rate. Determine probability of failure until next inspection interval, and determine most probable failure modes, whether it's a small leak, large leak, or rupture, and then determine the consequence of each scenario. And then finally, determine risk level. The RBI outcome would be an inspection and test plan and recommendation for mitigating risk. Reassessment means repeating above cycle all over again whenever input data and assumption changes. This is because risk and damage mechanisms are dynamic and changes over time. Inspection optimization. Reducing risk is like increasing the efficiency. With little effort, you can improve the efficiency significantly, but the ratio of effort versus efficiency starts decreasing until a point where efficiency can no longer be increased. Case of risk mitigation, by rearranging the inspection activities in line with damage mechanism and pattern, the amount of risk is reduced, initially significantly, steep curve, and then with a slower speed. There is always a residual risk that still exists. This is the risk that cannot be eliminated totally. In fact, with increasing the inspection, the risk of failure may increase. For example, due to intrusive inspection, ingress of moisture and environmental or polythionic acid into opening, damage to coating, etc. The residual risk can be attributed to the deficiency in design, human error, force of nature, sabotage, and the like. RBI should result in selection of most effective inspection method and frequency. Inspection methods are compared against cost and effectiveness, and the most efficient one is selected. So cost is not a factor, but here, if the most efficient one is selected regardless of the cost. The idea is to get the same level of risk mitigation with lesser cost if possible. Now, you have this graph with a risk and then a level of inspection activity. As you can see, if you increase the level of inspection activities, the risk reduces, but then on a steep curve, as you see here, but then it becomes like almost getting into a flat line. So there is not much benefit in increasing the inspection activity. Here, risk with typical inspection program is the upper curve, and the lower curve is the risk using RBI and optimized inspection program. And then there is, here you can see that there is always a residual risk not affected by RBI. It means that you cannot eliminate this risk. There is a amount that they always remain, residual risk. And actually, if you use a typical inspection program, if you increase the inspection, after some point, actually the risk of failure increases because you're opening, valves, cups, plugs, and then putting it back together. So in the process, you might have polythionic acid corrosion, or you might have, due to increase of moisture, you're actually disturbing the equipment too much. For example, if you do corrosion under insulation, you have to, if you want to remove completely all the insulation, then you might actually creating more damage here because you already exposed the vessel vulnerable by removing the insulation. Relative risk versus absolute risk. Determining relative risk needs considering a lot of factors and variables. This normally requires spending a lot of time and effort that is neither realistic nor cost effective, while gaining little in return. Hence, finding absolute risk is neither practical nor cost effective. That's why RBI is concerned about relative risk, not absolute risk. So using qualitative and semi-qualitative techniques, achieving risk estimates close to the actual risk. Introduction to risk-based inspection. Key elements of RBI program is based on the assumption that the few vital pieces of equipment in a process plant contribute to a majority of the risk. Consequently, if the high-risk equipment can be identified, then testing and inspection can be focused on them rather than several low-risk items. RBI helps to prioritize equipment for inspection, optimize inspection methods and frequencies, and develop an effective inspection plan commensurate with the risk contribution and equipment condition. There are 4 key elements for any RBI program: a management system for maintaining documentation, qualification of personnel, auditing to maintain consistency, and setting the requirement for input data. So that's like the sort of an infrastructure or the resources needed. So you need documentation, maintaining them, your qualification of personnel, and auditing to ensure that it's actually established whatever procedure you have, or the plan, the inspection plan that you have designed. And then document probability of failure, document consequence of failure, and the methodology for preparing the inspection plan and recommendation for mitigating risk. So if you look at this flow chart, risk is equal to likelihood of failure or probability of failure into consequence of failure. Now, likelihood of failure depends on age, on damage type rate, and inspection effectiveness, because if you can detect the crack, then you can, or the defect, you can repair it or remove it, and then thereby reducing the likelihood of failure. And consequence of failure could be depending on the type of failure. It could be injury, equipment repair, the business interruption, environmental effects, and then cost of equipment repair and shutdown. Consequence and probability for RBI. POF and COF are the 2 most important ingredients of an RBI program, but before that you need to list various possible failure scenarios and then determine the probability of each scenario as well as the consequence of it. The result would be the degree of risk you have concluded for each scenario. Obviously, inspection efforts should be directed toward monitoring and controlling ones with highest risk, that is, risk assessment would prioritize the inspection effort. Let's take an example in order to better visualize how RBI works. For example, the possible failure due to leak in a storage tank could result in one of the following scenarios: release of hydrocarbon vapor that could mix with the ambient air and ignite, release of toxic gas harmful to human or environment, or causing the equipment to shut down, losing revenue when it leaks. And then a scenario when the gas and liquid released are non-toxic and non-flammable, and therefore little harm done to human or damage to the environment. As you can see, a leak results in several scenarios. Now, if an amount of leak, small or large, is also considered, we have a greater number of scenarios multiplied by the probability of such leak ever happening. So as you can see, there are 2 equally important factors that are risk drivers, that is the consequence of failure and the probability of failure. For example, if the consequence of failure is great, but the probability of it happening is highly unlikely, such as a plane crash, the risk is low. Remember our previous example, I'm flying with an airplane where the consequence of plane crash is very grave, but the likelihood is negligible. making the risk of flying acceptable to many of us. On the other hand, there might be a situation where the probability of failure or leak is high, but the consequence is negligible. For example, leaking of a water pipe that has no significant cost, danger to human being or environment. According to RBI, the inspection efforts should be focused on high-risk areas where both the probability and consequence of failure are fairly high, producing high risk. API figure 2 on page 15 shows the result of 10 risks for an equipment. All the risks close to ISO line have the same risk level, although they may have different values for COF and POF. The ISO line is the reference line where any point above the line would be eligible for RBI assessment, that means unacceptable risk, and any point below the line is deemed acceptable risk. Please note that we are not only identifying and prioritizing those risks, but we are also identifying and accepting the remaining low-level risk below ISO reference line. So ISO reference line is the threshold or the line for acceptance of the risk. Or, as you can see, probability of failure, consequence of failure, you've got 10 scenarios, and you put the probability and consequence, so that coordinates XY shows the probability and consequence, and there is this line here, ISO risk line, and then 1, 2, and 3 are unacceptable, and the rest are acceptable. So this need to be addressed to mitigate it and bring it below the ISO risk line. So that's what RBI is about. Types of RBI assessment. The risk assessment may be qualitative, quantitative, or a combination, semi-quantitative. During risk analysis process, the approach from quantitative to qualitative or vice versa could change as long as there is consistency in methodology and input data. So you can change the approach, but the methodology should remain the same and input data need to be same, because the input data is what you base your RBI on it. And the methodology, if you change, for example, you change a software, we might have different results because the philosophy and the logic model on the software on a quantitative one is different, might be different. If the resultant risk assessment by RBI is below the maximum risk acceptable level, no further action is taken as long as the original input data remains valid. Qualitative approach. A qualitative approach is suitable when not much information is available or when screening a group of equipment in order to shortlist them. So it can be very useful during screening and to identify high-risk drivers initially and then zoom in on them. Qualitative approach depends heavily on the experience and expertise of the risk analysis team and hence liable to variation, because this is like judgmental. Any specialist can have his own opinion about that. That is why the quantitative approach is always more conservative and the result is descriptive. The qualitative approach is more conservative and result is descriptive or in ranges such as low risk, medium risk, or high risk. Quantitative approach, here the quantitative risk analysis uses facts and figures as input to the logic models and subsequently predicting events that could lead to the failure. Logic models have event trees and fault trees. Physical models are used to show how the events unfold or the speed which the event progresses. So there might be a question in the exam saying, what is a physical model? And the answer is, it shows how the events unfold or the speed which the event progresses. QRA analysis follows the same pattern as qualitative approach, but with facts and figures and a systematic way. Quantitative risk analysis activities include system and hazard, failure mechanism, identification, probability and consequence assessment, and finally the risk results. The QRA takes those parameters into account that could potentially change the probability and consequence of failure. For example, dike and drainage, fire and gas detection, fire protection, history of release, leaks, failure, previous history of consequences, injury to personnel and damage to environment, proximity to population, arrangement or of other equipment, and whether this might have a domino effect or trigger a sequence of events. Weather report, and finally hazard operability analysis or process hazard analysis result that identify the failing scenario and the subsequent mitigating actions taken. QRA can be used in RBI assessment by linking high-risk events to the equipment. Semi-quantitative approach means a combination of quantitative and qualitative approach using the benefits of both, the speed of qualitative approach versus the accuracy of quantitative approach. So this could be an exam question, that qualitative approach, is it accurate or is it speedy? Obviously, there is more speed compared to quantitative, or vice versa. The quantitative is more accurate, but it takes more time. And so the semi-quantitative is the most popular because it uses the benefits of both approach. And remember that there is a spectrum here in the purely quantitative and purely qualitative. It's never at the end of each spectrum. It's always somewhere here in the middle. And as you go from qualitative to quantitative, the details of RBI analysis increases, or vice versa. As you go to qualitative more, towards that, the detail of RBI analysis decreases. So this practically shows. Continuum of approaches, three RBI approaches, qualitative, quantitative, and semi-quantitative, are not competing approaches, but complementing each other. For example, qualitative approach can be used to quickly analyze the group of equipment, rank and shortlist them in terms of risk. High-risk items and equipment can then be scrutinized further with a more accurate quantitative approach. Please note that you can only compare the results of various types of RBI approaches or switch from one approach to another when the same or very similar RBI methodologies and assumptions were applied. So methodologies and assumptions are very important because they can change the result. Using different software may give erroneous results, as each software may use its own unique logic model. That's a methodology. The logic model is a methodology. The essential elements of inspection planning based on risk analysis is shown here. As you can see, a PDCA cycle, plan, data collection, risk assessment and ranking, do, implement risk inspection plan, and check mitigation, and then act again. So you have data, information and collection, consequence of failure, probability of failure, do the risk assessment, risk ranking, and then if the risk is not acceptable, then put it in inspection plan, do the mitigation, reassess, see that if it is within the acceptable limit or threshold, and then because this is a dynamic process damage mechanism and should be reassessment done every 10 years at least, or when there is a process change or there is change on initial assumption, then again you have to collect data and do the process again and again. So this is a PDCA. Precision versus accuracy. Precision and accuracy are often used interchangeably, but in science they have very different meaning. Accuracy is used for calibration and precision shows variation. And this picture, I think, greatly shows what is the meaning of precision. For example, here you have low accuracy, the variance in readings. Here you have high accuracy, but low precision. Is not exactly on the, hitting the bullseye. And here you have high precision, the readings are close to each other, but actually not hitting the bullseye. So low accuracy. Sorry, here you have high accuracy. It's actually hitting the bullseye, but its precision is not. I mean, like there is variance here. So precision show variations, and here you have bullseye, and all of them at the same point. So both high accuracy and high precision. The basis for predicted damage and growth rate or corrosion rate, the level of confidence in inspection data, for example, RT profile radiography has much better confidence level than UT spot thickness measurement, especially when non-uniform pitting corrosion mechanism exists. And the technique used to perform the inspection need to understand each technique pros and cons and limitation are all factors that should be considered. Quantitative risk analysis, although accurate, but can be erroneous because of the variability of input data, and hence should be cross-checked by expert judgment, that is qualitative analysis. So how you check the validity of the data? By expert judgment. Regardless of which type of RBI approach or combination of approach is taken, the accuracy of RBI analysis depends on using appropriate methodology, good quality of data or high confidence in data, and finally, assessment by qualified personnel for data validation. Understanding how RBI can help to manage operating risk, the mechanical integrity and functional performance of equipment depends on how well the equipment cope or how safe and reliable the equipment is under operating condition. Risk is not a fixed term, but is dynamic and changes over time. This is due to change in the circumstances such as process offset, equipment being idle or operating, startup and shutdown. So this is where actually most of the time where you have a violation of integrity operating window. Therefore, RBI process should be adaptive to changes. This means RBI major output, the inspection plan shall be updated accordingly. Management of risk. Risk management through inspection. Inspection is not directly reducing the risk, but is an information provided that reduces uncertainty and improves prediction of POF. So inspection is not reducing the risk, it improves the prediction of a probability of failure and reduces uncertainty. Inspection is used as a risk management activity for decision making. There are 4 factors that determine the probability of failure: damage mechanism, deterioration rate, how fast is deteriorating, whether inspection can capture those damages, and how large the damage can be tolerated by the equipment material under operating conditions. So the resistance of the material also is important about that determine the probability of failure. Using RBI to establish inspection plans and priorities. Inspection plan is a primary product of RBI. The inspection plan would address those equipment that are considered having unacceptable risk. The inspection plan shall describe the type, the scope, and the timing of inspection and examination recommended. So what type of inspection? What's the scope or boundary limit of inspection, coverage, percentage, and when you should do the inspection. Evaluation and fitness for service, FFS, is carried out as per API 579 to evaluate the inspection data results and determine whether it is acceptable to run the equipment or repair replacement needed. Most of the time they just ask you what is the FFS, which API used for FFS, and that's API 579. Other risk management, please note that not all risks can be managed through inspection. Examples are equipment reaching their end of life service. This can be an exam question that require replacement. There is nothing you can do about this, although you know that it's going to fail, but there is no repair or it's not very practical to do the repair replacement. Consequence dominated risk. So RBI is mostly about a probability of failure. You cannot control or the consequence part of the risk. Those you can calculate it, but you cannot control it. Those damage mechanisms that are event-driven happen under particular environmental circumstances such as chloride stress, corrosion of stainless steel, and damages with sudden failure such as fatigue and brittle fracture, because they are sudden and anyway most of the inspection techniques except metallography and all that, they cannot detect the fatigue limit. And if you see a crease crack, it starts at the surface. You can look at have an MT or PT and see, look at the cracks at the surface, which is an indication of fatigue. But by the time you find it out, 80% of the material is used up, if you are lucky to find it out. Relationship between RBI and other risk-based safety initiatives. Please note that safety initiatives from other tools such as reliability center, maintenance, failure mechanics, effect analysis, safety integrity level, layers of protection analysis, and PHA and PSM can be used as an input to RBI program. RBI program complements above initiative, so they are all for different purposes. Now let's go over see what is say PHA. The key provision of process safety management is process hazard analysis, a careful review of what could go wrong and what safeguard must be implemented to prevent. Potential hazards identified in a PHA will often affect the POF side of the risk equation. Process safety management. The major objective of process safety management of highly hazardous chemical is to prevent unwanted releases of hazardous chemical, especially into locations that could expose employees and others to serious hazards. See OSHA 1910, process safety management of highly hazardous chemicals. Equipment reliability. Equipment reliability is especially important if leaks can be caused by secondary failures, such as loss of utilities. So utilities, the equipment itself didn't fail, but because the utilities, for example, the water was not there to cool it down, so the water was cut off or the oil was cut off, so the equipment heated up and then burned. So it didn't burn by itself, but it burned because of the loss of utilities. This may lead to increased heat and pressure, failure of various gadgets, and eventually lead to equipment failure. Relationship with jurisdictional requirement. Please note that RBI can be applied whenever it is acceptable method and is permitted by applicable codes and legal requirements and not prohibited otherwise. Some codes and legal requirements prescribe calendar-based inspection, and the same should be incorporated within the RBI inspection plan, since RBI is a recommended practice and therefore cannot violate the mandatory codes nor the jurisdictional requirements and regulations. For example, most of the countries, they require that the cars should be tested for emission and brake and lights and for safety reason every year. Now, you cannot say that I've done an RBI assessment, the car is new and it's not needed. So you cannot contravene the law of the land. So same way for the vessels or any other equipment, if there is a law of the land or jurisdictional requirement that it should be done within, say, annual base or within so many hours, every so many hours, then that should be done. And I should be incorporated into RBI in the sense that once that inspection is done, so obviously the RBI inspection would be reduced.